Good morning, teachers and fellow schoolmates. I'm Chang Sik Fong from M21505, and I will be presenting to you my project, Language Modeling for Code Switching. This is the outline of my presentation for today, and I will start with an introduction to my project. Language models are used to assign probabilities to sentences. They have many applications in natural language processing, such as speech recognition and machine translation. For example, in speech recognition, given an acoustic signal O and a language model P, we aim to obtain the sequence of words W such that the probability of W given O is maximized. Code switching should actually be quite familiar to all of us. It is the phenomenon where a bilingual or multilingual speaker alternates between the use of multiple languages in the same conversation. For example, this sentence 过后它会 analyze 你的 speech is an example of a code-switched sentence. Singlish is an example of a code-switched language as it includes a mix of vocabulary from English, Chinese, other Chinese dialects, Malay, Tamil, etc. Now, we can state the goal of our project, which is to develop a language model that can handle the phenomenon of code switching. Having a good language model could help us in other downstream tasks. Now, I will move on to our materials and methods. We first segment the Chinese words, as Chinese has no word delimiters between words, unlike other languages such as English, which use a space token in between words. Segmented Chinese words often carry a different meaning from the individual characters. For example, Kai means open and Xin means heart, but together, Kai Xin means happy. It can allow our models to achieve better Chinese language understanding. When evaluating the model, we use the language model to assign a score to each of the sentences. The model is considered to have classified this set correctly if the original sentence was scored the highest. In order to generate alternative sentences, we converted the phonemes of English words and the pinyin of Chinese words to a common phoneme set. We then used a finite state transducer, or FST, to produce alternative sentences with similar phonemes. For the finite state transducer, we obtained Chinese word probabilities from the Mandarin Chinese news text corpus and English word probabilities from Gonen and Goldberg. Gonen and Goldberg had previously developed a language model for English-Spanish code-switched text. In this project, we have adapted it for English-Chinese code switching. To generate alternative sentences, we convert the words into phonemes, decode the sequence of phonemes into new sentences, which could be either English, Chinese, or code-switched, and allow minor changes in the sequence of phonemes to facilitate the differences between the languages. These steps can be easily implemented through composition of FSTs. We noticed that generated alternative sentences could sometimes still be linguistically correct, so we worked around this by only using alternative sentences that have at least two different words from the original sentence. This should increase the probability that the alternative sentences are linguistically incorrect. In order to generate alternative sentences, we require phoneme dictionaries, since the phonemes represent the pronunciation of the words. To be able to decode the phoneme and pinyin sequence into both English and Chinese words, we will need to convert both the phoneme and pinyin to a common phoneme set. Now, I will demonstrate the process of generating alternative sentences. First, we will convert the sentence into its phonemes, and the FST will return a string of words that has similar phonemes. Gonen and Goldberg found that discriminative training would allow the models to perform better than the generative baselines in their paper, and that they perform the best when trained on both code switch and monolingual sentences. Each training step is done over all the alternative sentences. They had used a hinge loss where for each set we trained the model to assign higher scores to the original sentence and the lower scores to the alternative ones, with a margin given by the word error rate between the sentences. The word error rate function is defined below. Here's a diagram of the LSTM model used by Gonen and Goldberg. The word embeddings are put through a bidirectional LSTM model. We then take the final output of the LSTM as the representation of the sentence and calculate a score from it. BERT is a masked language model that achieves state-of-the-art performance on 11 different NLP tasks in 2018. Unlike previous language models such as ELMO and ULM-FIT, which used LSTM, BERT is truly bidirectional uses word piece tokenization to break words down into subwords, and uses transformers rather than LSTMs, which deals with long-term dependencies much better. mbert was trained on the Wikipedias of 100 languages with the largest Wikipedias. We try to replace the LSTM used by Gonen and Goldberg with the mbert model. We use the first token of the mbert output as the representation instead, and calculate a score from it. Now, I will go through our results and discussion. Firstly, by testing our mbert model, we found that our mbert model performs better than the bidirectional LSTM model, and using two linear layers over the BERT results in the best performance of the mbert model. Through further testing using the McNema's test statistic, we also found that the use of layer normalization and ReLU did not have a significant impact on the model. Having a lower test statistic means that there is higher confidence that it had a significant impact. We found that the monolingual models perform better than mbert when the alternative sentences are all monolingual, so there are still some features of the languages which are not yet learned by mbert. Of course, we still need to use mbert when dealing with code switch sentences. Now, I will talk about possible future work and extensions. Firstly, one thing we had noticed was that the LSTM and mbert models rank Chinese alternative sentences higher than the English alternatives when the original sentence is code switched. We could try to do more tests to understand why this is so. Secondly, a recent paper by Liu et al. In 2020 had found that BERT reserves some implicit language information in the mbert embedding. They had also proposed an approach to remove this language-specific information, which could improve the cross-lingual generalization of the model. We could try to integrate their approach into the training of our model. Thirdly, we could also implement our mbert model in a downstream task, such as speech recognition on the CME dataset. We can then compare it with results from another recent paper by Luo et al. In 2020, which had used an LSTM model instead. In conclusion, our contributions are adapting Gonen and Goldberg's work to English-Chinese code switch data, proposed and implemented a new model based on multilingual BERT that outperformed their LSTM model, and used only alternative sentences that have at least two different words from the original sentence. Last but not least, I would like to thank my DSO research mentors, Dr. Chiu Hai Leong and Mr. Lim Jing, for their scientific guidance over the course of this year-long research project, Dr. Chiam Shi for providing the students with research opportunities and facilitating the entire research process, as well as my teacher mentor, Mr. Claude Chua, for his invaluable support. This is the end of my presentation. Thank you.